following on from the previous video, we got to this stage here where we've been given a surface. We're going to slice it at an elevation of 5, and then that will then give us this ellipse. That will then give us this ellipse. That will then give us this ellipse, and the equation for the ellipse is given by this. So punch that into Desmos. So jump to Desmos. So punch in the ellipse. So that's our equation here, and then from here we can use our parametric equations technique to turn it into a parametric form. So our x and y, the x and y location of our particle as it moves around, is given by this. So in a way, this is our position vector. So punch that into Desmos. So you would add your particle. So this is the location of our particle, which is this blue dot here, right here. That's our blue dot. So punch that in, and now as you slide A back and forth, you will always know the location of your particle. So our position vector is given by this. So you would go to add table, that this will then pop up, and then punch in the origin, and then this is our position vector in the x direction, in the y direction. So this blue line here represents our position vector. So going back to here, hang on. So once you've got your position vector, you would differentiate it. That will then give you your velocity vector. So now we need to add our velocity vector in Desmos. So jump back to Desmos, go to table, go to add, and then table. This green thing will pop up. Well, this thing will pop up. So this is our velocity vector. You would punch in the current position of your particle in the x direction, the current location in the y direction. So you would punch in the current location, which is this thing here, and then add your velocity vector. So add it in. So that should give you this, and the current location in the y direction of our particle, and then add it to our velocity vector, which would be this. So that this will then give us our green line. So this is our velocity vector. So as you move around, as you move A around, hang on. So you can see our position vector, and you can see our velocity vector. The velocity vector is always tangent to your path. Well, anyway, we would need to hang on. Let me pause this. We would need to work out grad f in our 2D world. So going back to here. So currently, hang on. Currently we're here. So once we're here, we can use our parametric equations technique to drive this particle around this particular path, this ellipse. So really we are currently here. We can use this t here to drive the particle around. So this is our function diagram, and using implicit differentiation, df by dt is given by this, and I'm expecting you to know this by now. Once you get to this stage, you can visualize it as one vector taking the dot product of one vector with another vector. This turns out to be grad f. This turns out to be our velocity vector, because dx by dt, dy by dt, which is our velocity vector. And because you're looking at a level curve where the elevation is always 5, that means df by dt is going to be 0, because there is no change in height. You're always at an elevation of 5. So this thing here equals 0. Now whenever you take the dot product of two vectors and it equals 0, it must imply that grad f will always be at 90 degrees to our velocity vector. So let me just illustrate this. Hang on. So grad f I'm going to show you how you can work out grad f later on, but grad f is that small vector there. So let me zoom in. Is that small vector there, and it's always at 90 degrees to our velocity vector. It's always at 90 degrees. As you move the particle around, you can see that it's always at 90 degrees to our velocity vector. See that? It's always at 90 degrees. So now let's have a look at how we can work out grad f here. So going back to here. So we need to work out grad f. We need to work out grad f. So looking at this, we need to work out grad f. So grad f is when you differentiate this when you partially differentiate this with respect to x. That will then give us this, and then partially differentiate this with respect to y. That will then give us this. So this is grad f in the 2D world. But we need to know the current location of our particle. We need to know the current location. So we would put this into here, and we would put our current location into here, and then that will then give us this thing here. So in Desmos you can't use t, because t clashes with because t is reserved within Desmos. So we've got to use a, and then a. So punch this into Desmos, and then it should give you your grad f vector. So going back to Desmos, you would go to add, and then you would go to table, and then this will pop up. Punch in the current location of your particle, punch in the current location of your particle, and then add our grad f, which turns out to be this thing here. So you might have to think this through, but that's, hang on, let me just enlarge this. So grad f is given by this, which you can't really see properly. I don't know how you enlarge this, but grad f is given by this. You might have to figure it out for yourself. So it's going to be 2 root 45 cos a over 45, and then punch in the current location of your particle, and then add grad f to it. Grad f turns out to be 2 root 20 sine a over 20. So that will then give us grad f. So this black line here represents grad f. So as you move it back and forth, hang on. As you move it back and forth, notice that grad f is always at 90 degrees to our velocity vector because of this thing here. When you take the dot product of two vectors, and remember there's no change in height because the elevation is always 0. So df by dt will always be 0. So you know that this vector will always be at 90 degrees to this vector. Okay.